Hi guys, welcome to my YouTube channel. In this video, we will be learning about binary search trees. Today, we will explore how BSTs works, their operations and time complexities. Without further ado, let's hop on. In this video, we will learn about what is a binary search tree or known as BST, key operations, code implementations and time complexity analysis. So, let's hop. Let's see what is a binary search tree. A binary search tree or BST is a special kind of tree where each node follows these rules. Left subtree of a node contains only nodes with keys less than the node's key. Right subtree of a node contains only nodes with keys greater than the node's key. The left subtree and the right subtree should be binary search trees. So as you saw, the left subtree and binary subtree must be binary subtrees because binary search tree is also a binary tree, so it must contains all the necessities that must be completed to be a binary tree. Binary search trees has four main operations: insertion, adding a new value; deletion, removing a value; search, searching a value to find its existence; traversal, visiting all elements. So let's see how the code implementation works. Okay guys, let's see how the coding works. I already implemented the code to save time, but I will be teaching all the components in this code thoroughly. So let's go on. Our code starts with a class called BST. Inside it, we have an inner class called node that stores three things: an integer, key, and reference to the left and right child nodes. The constructor of node simply initialize these values. The BST class has root variable, which points to the topmost node of the tree. In the constructor, we set it to null because at the beginning the tree is empty. Now for the insertion. The insertion method calls the helper method insertRec. If the current root is null, we create a new node with the key. If the key is less than the current node's key, we go to the left subtree. If the greater, we go to the right. This keeps the binary search tree's priority intact. See? In here. If the root is equal to null because it's empty. And the root new key, node key, and root is returned. And we put the function if the key is less than the root, then it's go to the left side. If the key is greater than the root, it's go to the right. For this search function, searching works in a similar way with searchRec. If the node is null or if the key matches the node's key, we return it. The node's key. Otherwise, we move all left or right, depending on whether the key is smaller or larger. This makes searching efficient in the balanced tree. See, in this if notation, if the root is null, then we return the root because it's null. If the key is less than the root, then we go to the right side of this subtree. Sorry, left subtree. Then if the key is greater than the root, then we move to the right subtree. For the deletion, the most interesting part, we must first search for the node. If the node has no child, we just remove it. If it has one child, we return that child as the new link. If it has two children, we replace its value with the minimum value from the right subtree and delete that minimum value node. Minimum value. Now, to find the minimum value, the min value method simply goes all the way to the leftmost node, which always holds the smallest value in a BST. Now for the traversals, we need to find two types, in order and pre-order. We also get to find the post order also. We have three traversal methods: in order, left, root, right, and the pre-order, root, left, right, and the post order, left, right, and the root. And for the main method, this is the main method, public static void main. We do create the main method. In the main method, we create a BST object and insert 50, 30, 20, 40, 70, 60, and 80. And for the print statements, we put the first print statement as in order traversal, the second as the pre-order traversal, the third as the post-order traversal. In the next line in the print statement, we are going to search for the 40. We are going to search 40. Then we are going to search for 90 if 90 is available. In the print statement, we are going to the next print statement, we are going to delete 20 and see the in order, post order, and pre-order. After that, we are going to delete 30 and see the rest of the orders. And also the same goes to 50. So let's see how the code runs. Okay, now we have got the output. The in order traversal, we have got 20, 30, 40, 50, 60, 70, 80, which is also in the correct ascending order. In the pre-order, we can find the root node first. So in order, we can find the root node in the middle. So in the pre-order, 50 is the root node, and the in order 50 is also the root node. In the left side of the 50, we can see 40, 30, and 20, which are all less than 50. In the right side, 60, 70, and 80, which are greater than 50. So in the in order traversal, we can find that the BST traversal tree is balanced. In the post order, we can find the root node at the end of the traversal. For the search function, we searched for 40. We got the value as true because 40 is available in the tree. And when we search for 90, it returns as false because now 90 is available. In the delete, when we delete 20, we can see that 20 has been deleted. So no 20 in the inverse in order travel, pre-order travel, or in the post-order travel. When we delete 30, it also got missed. It also has been dropped. But when we delete the root node, which is 50, previously which was 50, has been changed to 60. In order, we can find 60 in the middle. To confirm that it is the root node, we can see in the pre-order, it is in the first row, and in the post order, it is in the last column. So as you can see, in this way we can justify that the BST search method completely works. Now let's move to time complexity. For the time complexity, we must complete two things. best average case or balanced BST, and the worst case unbalanced BST. For a balanced BST, insertion, search, and deletion takes big O log n time. Traversal in order, pre-order, and post-order big O to the n. And the worst case, unbalanced BST. When the tree is unbalanced, these operations can degrade to big O n. Traversal takes big O n as every node must be visited. That wraps up our overview of binary search trees. Thank you for watching, and I hope this helped you understand BSTs more clearly. So, for more videos related to BSTs and data structures, follow up my channel and subscribe. Peace out.